space and astrophysical plasmas, and it's simply a twisted bundle of magnetic field lines. And the key things perhaps about why they're useful is they are definitely non-potential magnetic fields, so they have currents, and therefore they are reservoirs of magnetic energy. And there's many reasons to believe that twisted fields are sort of quite common in the corona, either because fields emerge ready twisted, or you can drive further twist by rotating the foot points, and they're involved in eruptions and in other events. And in some sense, this is the sort of simplest non-potential structure that you can have. And obviously you can build more complex structures above that. And a lot of the motivation of what I'm going to talk about is about solar flares. These are, of course, the most powerful explosions in the solar system, and they release huge amounts of stored magnetic energy and have a signature right across the electromagnetic spectrum, from radio waves to gamma rays, and more or less everything in between. And this is created really both by strong heating of the plasma, so we get very hot plasma, 10 megakelvin or more, and also lots of non-thermal electrons and also ions, although we see the electrons much more. And I am going to be talking both about the origin of the hot plasma, about the heating, and the non-thermal particles as well. And one reason for being interested in this, apart from the fact that it's just intrinsically interesting, is that the radiation and the high energy particles from flares can have significant effects on the Earth and our space environment. So really flares are the beginning of what we call space weather. I'm not going to sort of say much more about space weather because that would plainly be like another talk in its own right, but it is a sort of motivation behind what we're talking about here. And in terms of underlying physics, the key physical process that again is sort of really going to be going on throughout everything I'm going to talk about in this talk is the idea of magnetic reconnection. And reconnection in its simplest form is the bringing together of oppositely directed field lines. And the key feature is that it involves a large-scale ideal region in which the field lines are frozen into the fluid, but there must be some kind of localized dissipation region or current sheet in which the frozen-in condition is broken. And the important things about this for our purposes is that it's quite a rapid process, and it does two things. It changes the magnetic topology or restructures the magnetic field, and perhaps even more importantly for what I'm going to talk about here is it converts magnetic energy into thermal and kinetic energy. So it's a process for converting magnetic energy particularly into heat, but also kinetic energy. And of course, it's well known that magnetic reconnection is likely to be behind the release of stored magnetic energy in solar flares. And the cartoon here is just the sort of standard flare model. Although in fact I'm mostly going to be talking about a slightly different flare model, not an eruptive flare as is sort of shown here. But you can see in this standard model the twisted flux rope, which is erupting in this particular model, and the reconnection, which is causing the sort of heating and so on, at least as an ultimate source. This is also closely related to the idea of coronal heating, and as one more theoretical concept before we get more into the main part of my talk, I want to introduce the idea of relaxation. And so we know that in the corona we are constantly building up free magnetic energy through photospheric motions, twisting or other distortions of the fields. And if it's slow, the corona will generally be close to a force-free state. But a very old idea is that force-free state will then tend to relax, conserving helicity and releasing free magnetic energy, which can then heat the plasma. And this, say, theoretical concept will be, in some sense, behind quite a lot of what I'm going to talk about. But there is a crucial kind of gap in this initial ideas of relaxation, and that is that you actually need the free energy to build up between relaxation events. And you can see that very much in a flare. In a flare, it's not enough just to explain how the energy is released. You know, why do you get reconnection? Why, and how does that work? You also need to explain almost why it didn't get released earlier. So we also need to explain the build-up of energy as well as the release of energy. And therefore, we need to define the trigger for when a relaxation or an energy release event happens. Now, I'm sure there's not necessarily a single answer to this question, but I'm going to talk about one idea of what determines when this relaxation happens. So energy builds up, and then you have a flare, or maybe, you know, on a smaller scale, a nanoflare heating the corona. So we need to talk about the trigger as well as the energy release. So one possible idea, and I say not the only idea, is to start talking about the kink instability, which is well known in plasma physics. And in the kink instability simply happens if the magnetic field is too strongly twisted. And you can do this yourself at home if you have a rubber band. If you twist and twist a rubber band, if you keep twisting it, you'll see it starts to develop sort of knots or kinks. And that basically is the kink instability. And way back, many years ago now, me and Moni van der Linden proposed that the trigger for relaxation or energy release was the onset of the ideal kink instability. And then you would get the helicity conserving relaxation during the non-linear phase of the instability. And the kink instability is indeed quite widely observed in the corona, or at least inferred. There's these very nice observations back from 10 years ago from Srivastava et al. Showing a kink instability in a confined flare. You can see the sort of kind of twisting kind of building up, and then the loop kind of brightens and then relaxes. And there are many other observations. I've listed just a few papers here which in some way show kink instability in flares or erupting prominences. And here is an example from just one of them, showing a very nice sort of extrapolation of a twisted flux rope which goes unstable. And it also, of course, is widely observed in experiments as well. And in some sense, the structures seen in some of the experiments are quite similar to what I'm going to be talking about in coronal loops. And here again, we see not just kink instability, but also relaxation or reconnection associated with the nonlinear kink. So coming back now to the solar corona and some theory, let me just briefly say what our methodology is. And really our aim is to bring together global scale fluid processes and small scale kinetic processes. We can't, of course, do this perfectly. Frankly, nobody can, yet anyway. But the way we do it is to combine 3D MHD simulations, mainly with Lair 3D. So unless I say otherwise, all the simulations I mention here will have been done with Lair. And we combine that with test particles using a guiding centre approach, strictly relativistic guiding centre, at least usually. And although this is in clearly a lab plasma, I like this little picture showing you the guiding centre of the gyrating particles. So what we calculate is actually this red line, which averages over the fast gyro motion of the particles. And importantly, when we track our particles, we track them in the fields from the MHD simulation, which is evolving in time. So we take essentially the electromagnetic fields at the sort of position and the times where the particle is, obviously interpolating from the MHD grid. And it's the combination of these two, MHD and test particles, that's behind the rest of what I'm really going to talk about. So going back then to the kink instability, we did early simulations which really verified the idea that a kink unstable loop would relax. And so these are 3D simulations. You can see the loop kinking. The red, it starts to develop a current sheet in the nonlinear phase. And then as things develop further, that current fragments into sort of many, many small current sheets throughout the loop volume. And that allows lots of reconnections and the loop essentially to relax to a much lower energy state. So this was a slice through the middle of the loop, just cutting through the middle, and you can see the current sheets, which is now broken up into many current sheets, and also the rather complex flows associated with the sort of reconnection outflows from those many current sheets. And so we found there was reconnection both within the loop through those current sheets that I've shown you, but also reconnection of the twisted loop with the surrounding untwisted field, which caused the loop to sort of expand and untwist. And this is shown in a similar, just a different visualization, showing you the kink unstable loop starting to relax and ending up with a weakly twisted and somewhat larger field. And following on, and this we showed was very much associated with a relaxation to a constant alpha or Taylor state. So we have multiple reconnections which kind of mix up the profile of alpha and cause this relaxation, therefore releasing magnetic energy, and of course that mainly goes into heating the plasma. So the energy goes down, the plasma heats. And also, because we've got these current sheets, those current sheets are also very good, they've got electric fields, so they are good sites for accelerating charged particles. And this is some early work in which we filled one of these loops with test particles, protons on the left and electrons on the right. And over time, the loop basically filled up with energetic particles. So because the current sheet is fragmented, it's a very efficient particle acceleration mechanism, which accelerates particles sort of throughout the volume, not just at sort of one single site. So these were obviously rather idealized models in lots of ways. For example, they're cylinders, and that we started with an unstable state. So from then on, we moved on to looking at, in some ways, more realistic models, something that looks a bit more like a real coronal loop, and looking to forward model the observational signatures. So we really want to say, well, what would you see if this process was going on, and can we in fact detect it? So we sort of developed a model now taking a sort of curved magnetic loop. So we started with an initial dipolar field and just kind of twisted up the foot points. And just like the cylindrical loop, that does eventually kink. It goes kink unstable. And we get somewhat similar behaviour. And then we coupled this to relativistic guiding centre simulations of test particles to model energetic or non-thermal electrons and ions. So we've got both the MHD and the kinetic particles. So this means we can predict various thermal and non-thermal emission. And of course, there's spatial and temporal variation. So this is all in 3D and varying in time as well. And a kind of series of papers has sort of looked at this, so I'll just skim through a little bit of it. This shows you the magnetic field and also the currents, and you can see the kink instability developing, but this time, because it's sort of curved, the field now develops this large-scale reconnection as well, in which it kind of bends back on itself and then reconnects. And you can also see the generation of currents, and again this fragmentary current structure, but also currents concentrated at the foot points and the loop top. And looking at the loop top in sort of cross-section, we were able to identify clearly a sort of single reconnection site. So this is just a blow-up of the current sheet at the top of the loop and showing that you've got sort of localised reconnection. But of course this is just one. There is reconnection going on in many other places as well. So this is more or less a series of stills of kind of the same thing. And associated with the reconnection, as you might expect, the magnetic energy drops off and then sort of flattens. So we have this relaxation associated with the multiple reconnections, and then relaxing to a lower energy equilibrium. The plasma heats, and during the reconnection activity, the kinetic energy kind of peaks associated with sort of reconnection outflows, and then drops as we reach a new equilibrium. So if we start to forward model what we might see, this was with Rui Pinto, and we visualised the thermal emission due to the heated plasma. So this comes from the sort of MHD. And one of the interesting things there is you can see that although the magnetic field is quite strongly twisted, you don't really sort of see that in the emission. And that's really because the plasma only is heated after the twist has gone away. So you see sort of weak twist, but not as strong as was in the initial field. In the same model, we also were able to predict light curves of both thermal and non-thermal emission. So the thermal emission is relatively long-lasting and smooth. The non-thermal emission, the hard X-rays, are quite sort of spiky and of shorter duration, as indeed is observed. And we also could predict the locations of sort of hard X-ray sources, because we've got the electrons, you can calculate the hard X-rays. So this is a sort of top-down view, this is a side-on view. And you can see we get generally foot-point sources, but sometimes loop-top sources as well, as indeed is, can be observed. So we then wanted to answer the question of, can we actually detect whether the field is twisted? Because, as I said, the twist doesn't show up very well in these models from the either the hard X-rays or the soft X-rays. So we considered microwave polarization as a possible way of actually seeing magnetic twist. And the idea is microwaves come from gyrosynchrotron emission, which is electrons gyrating in the magnetic field. And they will therefore be polarised parallel to the line of sight magnetic field. And if you think of a simple twisted field, depending obviously on which way you look at it, you can see the line of sight will either be sort of towards you or away from you. And in a simple view, that gives this very characteristic pattern of the direction of the line of sight field, and hence the polarisation of the microwaves. But the question is, could you see this in reality when you take account of the complexity of the energy release, the fact that the field isn't a simple cylinder, things are varying in time and so on. So what we did is we used our simulations together with the GX simulator, which calculates gyrosynchrotron emission, and we took the fields and densities and so on from our simulations, added some non-thermal particles. This is just one example of what we found. So this is looking at what we called a weakly converging loop. And you can see this was a sort of top-down view, and this is a side-on view. And the key thing here is the Stokes V, which is the polarization. And you can see, actually, particularly in the sort of, as it were, the side-on view, the loop on the limb, that at least in higher frequencies, you can see this characteristic stripe, which is an indication of a twisted field. And some evidence from the sort of on disk view as well of the sort of characteristic diagonal, which again is characteristic of twisted fields. So it suggests this can be used at least at higher frequencies. And more recently, there have been some observations which do suggest evidence of twisted fields from microwave observations. We also had a look at something, plasma motions, non-thermal line broadening. And interestingly, we did this in 2016, and now Pontin et al. have done sort of quite similar predictions, but for a braided loop. But in our unstable kinked loop, what we did is we calculated the velocity dispersion. So that's the, as it were, the part of the velocities which differ from the bulk flows, and then saw how this integrated along the line of sight. And these are quite complicated plots to look at, but the simple take-home message is that we found correlations of the non-thermal, sort of, which would give you line broadening, the non-thermal velocity dispersion with temperature. So the hotter plasma has also stronger non-thermal flows or turbulent flows. And this is characteristic, we think, of turbulent flows basically being created by these multiple reconnections. So it's the reconnections that are creating the flows, and that is also, of course, heating the plasma. But I say this is not very distinctive of whether the loop is heated by a kink instability or braiding flows, say more generally characteristic of reconnection in general. So very recently, we have also started to consider the idea of we could get waves or oscillations in these loops, and that these waves, well, we can see these waves again as a signature of reconnection. So we have again looked at microwave emission, but now considering the time dependence of that and whether that can pick up oscillations. So we've taken a similar loop model to what I've shown you before, and we've looked at looking across lines of sights at the foot points and the loop top. We have put in non-thermal particles, which are sort of spread along the field lines, but heated in regions of high electric, accelerated in regions of high parallel electric field. And we are really trying to answer the question of, well, will there be oscillations, and will we be able to see those oscillations in the microwave emission? So, first of all, I say we've done our MHD simulation, we've added the non-thermal particles, and then we've looked across lines of sights in these, picking essentially these three locations, and see what the gyrosynchrotron emission turns out to be. So these are the actual light curves at the left foot point, the loop top, and the right foot point in one particular frequency. We actually calculate a series of frequencies, but this is the lowest, the 4 gigahertz. And you can see, as you'd expect, the emission kind of rises as the reconnection kicks in and the particles get accelerated, and then sort of gradually dies off as the accelerated particles sort of die away. But you can also see, even in these overall light curves, there is signs of some kind of oscillatory behaviour as well. It's not simply just a smooth rise and fall, particularly visible at the loop top, but there's some evidence of oscillations at the foot points. Oh, these are wrongly labelled, sorry, you can see that this is actually left foot point, right foot point, and loop top, sorry. So obviously these two labels should be switched round. You can see the foot points are obviously quite similar to each other, but not identical. So then what we did, and this is with my student Chris Smith, is we detrended those so we can see the oscillations. Again, sorry, the labels here, they're the same ones, so they should be. This should be the loop top on the right, and this is left foot point, right foot point, and loop top. And actually probably the loop top is the one to focus on. We did this again in a series of frequencies, but I've just shown a couple here. And we have, particularly at the loop top, these quite characteristic oscillations with a relatively long period, which are obviously sort of MHD oscillations. But at the foot points, there's also some sort of much shorter period oscillations as well. which we think are associated with sort of intermittent reconnection, perhaps to do with the anomalous resistivity. And these, of course, for those of you that know about these things, are very similar to observed quasi-periodic pulsations in flares. But perhaps the important thing about these results is we are getting very clear oscillations, but we have not driven this in a sort of oscillatory way. We haven't, as it were, shaken the foot points. We've simply driven it in a slow, steady way and then just let the loop carry on reconnecting. So these are basically self-oscillations. They're sort of driven within the loop rather than due to any outside oscillatory driving. So far I've focused on a single flux rope, a single twisted magnetic flux rope. And I want to move on now to more complex structures in which flux ropes start to interact with each other. And this brings me to the idea of avalanches. So if Louise is still there, I'm sure she'll know all about avalanches. So we want to talk about the idea of avalanches in the corona. Now, of course, we're not saying there is falling snow in the corona or anything like that. But the idea is, in an avalanche, a little bit of snow falls down, pulls a bit more with it, and then that pulls more with it, and then a lot more, and so on. So the first little snowball falling down is a kind of trigger of a much bigger event. So we wanted to consider if the same thing could happen with unstable magnetic fields. So we noted the fact that the coronal magnetic field has a multi-thread structure. There won't just be one twisted thread, there may be many twisted threads with different twists. And so originally we asked the question, is if you have a single unstable twisted thread, which as we know can go unstable and release its energy, can that trigger energy release in stable neighbours and potentially lead to a large heating event? Well, of course, the answer would be no. It probably wouldn't have been very interesting. So the answer, of course, was at least in some circumstances, yes. And so the original simulations we did with Alan Hood and his student Tam at St Andrews was we considered two loops, one of which was kink unstable and a neighbour which was twisted but kink stable. And it depends on how close the loops are together, but what can happen, you can see first of all this loop goes unstable, and this is exactly what I showed you sort of early on in the talk. The kink instability develops, you start to get reconnection, energy release. This loop is on the left is stable and so does nothing for now, but at some point, because it's expanding, as I mentioned early on, this loop sort of bumps into its neighbour, and as soon as it does so, the two loops interact and merge, and the whole thing then relaxes to a new sort of equilibrium state. And if you look at this in cross-section, so this is sliced through the middle of the loops, so I've just taken a slice through the mid-plane and looking at the current. Well, if the loop's too far apart, basically the unstable loop goes unstable as before and the stable loop does nothing. But if they're sufficiently close, you can see the first loop going unstable, and then at this point here, it kind of bumps into the stable loop and then very rapidly kind of eats it up. And importantly, we get the energy out of the stable loop as well. So in this case, not only do we get the energy out of the unstable loop, but we extract the energy from the stable field. So you get much more energy out from just one kink instability. We then extended this from 2 to 23 loops, as you would, the obvious next step. So this shows you a sort of, again, a cross-section of these 23 loops. Only 3 of them have had their field lines plotted, otherwise it would look a total mess, but there are actually 23 of them. And only the central loop here is kink unstable, so it's slightly more strongly twisted. And I'm sure many of you have seen this movie before, but I can watch it over and over again. And you can see what happens is the unstable loop again sort of goes unstable, and then gradually bumps into its neighbours and sort of eats them up one by one. And every time a new loop gets sort of eaten up, there is another burst of energy. So we have a very bursty series of energy releases, which is perhaps reminiscent of a nanoflare storm. So you could say you've got a storm of nanoflares and a big burst of coronal heating. We also showed that if you put in oppositely directed flux ropes, that sort of blocks or at least slows down the avalanche. So this has been developed in a number of ways. My student Asad Hussein developed a relaxation theory model of this. So using the idea, going back to Taylor, that you could consider, you have your two initial flux ropes, these relax into a single flux rope, conserving helicity but releasing energy. And it turned out this agreed really rather well with the simulations. So he applied relaxation theory to the same sort of conditions of the 4 simulations that we did for the MHD, and the energy releases agreed really very well in the sort of 4 possible different cases. And so we then tried extending that to the 23 loop simulation and simply making an assumption that each relaxation took the same time. We found that we got this sort of stepwise drops in energy, which again rather nicely matched what came out of the MHD simulations. We were also able to show with James Threlhall that these avalanching loops were very effective at accelerating particles. So if you inject test particles into these loops, this is it going back to 2 loops, one stable, one unstable, we find that, as you might expect, first of all you accelerate particles in the unstable loop, but as the loops interact you accelerate particles sort of throughout the volume, and you end up with a very nice power law non-thermal tail of accelerated electrons going up to energies of MeV. But of course in these things we'd started with one loop being unstable, and that is a bit unrealistic because, you know, how do you ever get to a loop being unstable? You know, you can't create an unstable loop from sort of nowhere. It has to evolve through driving. So really what would be more realistic would be to start with a potential field and actually twist the fields until at least in one part it goes unstable. So this is what Jack Reed did, and I think Jack is in the audience here if he hasn't gone away. So what Jack did is he started with 3 loops. So we have a sort of symmetrical situation, one of which is twisted a little bit faster than the others. Or I should say he started with a potential field rather and created 3 loops by applying a twisting pattern in which one twist is a bit faster. So you form a central loop which kind of goes unstable first. And essentially the behaviour is quite similar, again, in that the central loop goes unstable. Even though it's evolving, it's driven rather than just starting in an unstable equilibrium. And then it bumps into its neighbours again, which are not yet unstable, and the energy of all the loops is released. And then we persist with the driving, and you can see we get a sort of series of bursts of energy release. So this is like the first loop going, the second one going, the third loop going, and then ongoing bursts of activity. And this is associated with very nice, you can see the reconnections between the different field lines. So initially, as you twist them, the sort of field lines just kind of rotate. But as you get reconnection, the ends of the field lines, as it were, jump as one field line jumps to what connects with one connected to a different foot point. And eventually we get this very strong, if you like, mixing of the ends of the field lines. So what's done here is you start at one end of the loop and you track the field lines to the other and sort of see where they end up. And I say the more reconnection you have, you can see the field lines become, as it were, much more mixed between their original positions. And I say that's associated with the reconnection and, of course, with the energy release. So, as a sort of postscript to this, and I'll then come very briefly to stars, we have wanted to take these concepts and this methodology onto, rather than discussing just generic events, which is everything I've done so far, these are not particular flares, they're just very idealised generic models, to look at an actual real flare. And so what we've done in collaboration with Kusano and San and Inui-san in Nagoya is consider an individual flare in which the MHD evolution has been previously modelled using nonlinear force-free field and then an MHD simulation. And we've added to that non-thermal particles to see how the non-thermal particles evolve in this flaring event. And here you can see the magnetic field evolution, but we are able to identify where there is a region of strong electric field, where the sort of loop structures are interacting here, which is where most of the particles are accelerated. And then in the electric and magnetic fields, we track the electrons and protons. We see they become accelerated, as you'd expect. This is the spectra evolving in time. So you can see the development of non-thermal tails in both the electron and the proton distributions. And because we can track particularly the electrons and see them impacting on the chromosphere, we can also forward model hard X-ray sources. So these are hard X-ray sources modelled at different times in the event. And we can see that particularly these two sources here are also seen in RESI, at least pretty well. The crosses are where our model predicts, and the contours are RESI contours. Interestingly, this source here, which is somewhat weaker, is not seen by RESI, but there may be reasons for that. Maybe it's too weak to see, or whatever. So this is something we're pursuing now to look at a much larger group of events using this methodology. Well, I promised to say something about stars as well. So I'll just deal with that very briefly and therefore leave a bit of time for questions. So obviously everything I've talked about so far has been in the solar corona. But the sun is just one star, and other stars have flares as well. And a particular group of stars that are interesting because they have actually rather big flares are T Tauri stars, which are young stars, ones which haven't yet joined the main sequence. And they have particularly sort of virulent or violent flares. And so with my student Charlotte and my colleague Gary Fuller, who's basically a radio astronomer and an expert on young stars, we started to develop some models of radio and X-ray emission from T Tauri flares. And our starting point was to consider the Gödel-Benz plot, which considers the correlation between radio luminosity and X-ray luminosity. And this is well known that there's a very good simple scaling relation which applies to solar microflares, to solar flares, to main sequence stellar flares. But when we collected all the data for T Tauri stars, we found that it sort of lay a bit off the plot. So in other words, they are sort of overluminous in radio. And so we started to try and develop a model which, at least to some extent, explains this. So our idea was that the flares in T Tauri stars would be due to large loops in which a loop extends to the disk or the remnant of the accretion disk, and some kind of reconnection where the very large loop interacts with the disk would be the source of the flare. So we modelled these very large loops. So we considered a large loop and filled it with hot plasma and non-thermal electrons, and then calculated both the X-rays and the gyrosynchrotron that you'd get. So I'll sort of skip through the details, but here's one example of a set of our results from our first model, in which we considered a sort of the way in which the parameters might reasonably vary. This is magnetic field, this is thermal density. And we did find over this sort of grid of parameters that the spread of points agreed rather nicely with the observed spread, and did indeed lie sort of just under the Gödel-Benz relation. So we then developed this. Now we wanted to consider time-dependent models rather than just static models. So we took a MHD simulation of a T-Tauri flare done by Orlando et al., and we worked with them, with Orlando and Real, to put non-thermal particles and calculate gyrosynchrotron emission in these simulations of a flaring event. So it starts with a dipole field. The flare in this model is described as just an injected heat pulse, which then evolved to give a large flux tube. And I say what we did is we put non-thermal electrons into this flux tube, allowed them to be sort of distributed along the magnetic field lines, and this is our flux tube, which is defined by the sort of heating event, and the different colours just to scale for the density of non-thermal electrons. So we can see how those spread along the field lines and how that evolves in time. And we calculated the spectra, the radio spectra at successive times, and we get a sort of characteristic bump associated with the flare, which kind of goes up and then obviously eventually dies away again back to a effectively thermal spectrum. And we also predict light curves in the various radio frequencies as well as in radio. So the challenge would now be to look for this characteristic bump in radio measurements as a signature of the non-thermal particles and the gyrosynchrotron. And some efforts have already been made for this, but we're hoping that will be done in future. So to summarise then, I've shown you that we've used a combination of MHD simulations and test particles to look at particle acceleration and heating, particularly focusing on the kink instability of twisted flux ropes, which generate these fragmentary current sheets and a very efficient heating. We've looked at the various thermal and non-thermal emission, which could be used to detect the twisted fields, and then extended this to consider interacting flux ropes, avalanches, in which it turns out you only need one little flux rope to go unstable, and you can get energy out of all the stable neighbours. And finally, much more simple models, but the first models ever looking at the origins of gyrosynchrotron emission in young stars. So I'll stop there, and hopefully there'll be some questions.